Due to COVID disrupting students' education for the 2022 summer GCSE exams, the exam boards have released an advanced notice article that gives an insight into what will be on the exams this year. I'm sure your teachers have shown you this article already. In this version of the advanced notice article, I'm going to show you anything in green is definitely going to be on the exam. Anything in yellow may be on the exam in a small way, and anything in red will not be on the exam. In this video, I'll go over the green and yellow areas to help you prepare for the Triple Physics Paper 1 exam. Good luck. Right, so I'm going to go over the Advanced Notice Triple Higher Physics Paper 1 for the Edexcel exam for 2022. Right, so anything in green is going to be a major focus and will be assessed. Anything in red will not be assessed, and anything in yellow may be included, but it's not a focus. So it'll either just support your understanding of the green areas, or it'll just be worth the odd 1 mark. And I'm only covering the higher in this exam. So from SP1, the motion unit, and SP2, forces in motion, you've got to be able to explain that a scalar quantity has magnitude or size, but no, that should say specific direction. So you literally just get 1 mark in an exam for saying that a scalar has size only. You're also supposed to be able to explain that a vector quantity has both size and direction. So that could be worth 2 marks. You've got to be able to explain the difference between vector and scalar quantities. Well, that's basically what I've just explained there. A vector quantity has size and direction, but a scalar quantity has only size. You've got to be able to recall vector and scalar quantities, including, so I've underlined the vector in red and I've underlined the scalar quantities in orange. So displacement is basically a distance, but it has a direction as well. That's what makes it a vector. A speed is a scalar. It has only size, but the velocity has size and direction, so it's a vector. Acceleration is a vector. Force is a vector. Weight is a vector. Mass is the equivalent scalar. Momentum is a vector. And energy is a scalar. So there's plenty of examples there if they ask you for some examples of vectors and scalars. You've got to be able to recall that velocity is speed in a stated direction. You've got to be able to use the equation to calculate speed by doing distance divided by time. You'll be given all of the equations this year, by the way. You've got to be able to calculate distance by doing speed times by time. You've got to be able to analyse distance time graphs, including determination of speed from the gradient. Right, I've just expanded on that a little bit for you. So a distance time graph, obviously distance goes up the side, time goes along the bottom. Make sure if you're doing the graph to put the units in. Now, basically, if it's a steep slope, then that means it's fast. And if it's not as steep, that means slow. Now that's basically because in the same amount of time, 10 seconds, this object, this car or whatever, has only managed to cover 10 meters of distance, whereas this car has covered 20 meters of distance. You also need to be able to calculate the speed from the gradient. So to get the speed, just do the distance over the time. So you can see from this area here, it's travelled 20 metres and it took 10 seconds. So 20 metres over 10, that would give us 2 metres a second. Whereas for this slower car or whatever it is, speed is distance over time, it only did 10 metres in 10 seconds. So that's only 1 metre per second. You need to be able to recall and use the equation for acceleration, which is basically acceleration equals the final velocity v, take away the initial velocity u, divided by the time. So this equation relates acceleration to the time. You should also be able to relate acceleration to distance, and in which case you'll need to use this equation. V squared minus u squared equals 2 times by a times by x, where x is the distance. And you should be able to analyse velocity time graphs to compare acceleration from the gradients. I'll show you that in a second. Calculate the acceleration from the gradient and determine the distance travelled using the area between the graph line and the time axis. So let's have a little look at the acceleration first. So you can see that once again, if it's a steep line, that means it's large, but this time it's a large acceleration, not a large speed. If it's flatter, that means it's a small acceleration. And in order to get the acceleration, we'll use this equation. Acceleration equals v minus u over t. So v is the final velocity. So you can see here the final velocity was 20 meters a second. The initial velocity for the full slope was 0 meters a second. So 20 take away 0, and all of that change in velocity happened in 10 seconds. So that comes out as 2 meters per second squared. Make sure you get the units right. And this smaller acceleration, you can see the car has only gone from 0 to 10 meters per second in the same amount of time. So it's only got half the amount of acceleration. If they ask you to work out the distance travelled from a velocity time graph, then you just calculate the area under the graph. So for this first section, when the car or whatever has got uniform acceleration as represented by the straight line going diagonally upwards, you can see the shape it forms is a triangle. And in order to get the area of a triangle, you do a half times by the base times by the height. So that's a half times by the height was 10 times by the base was 5, and that comes out as 25. For this section here, where there is no acceleration, rather we've got a constant speed of 10 meters per second, the area under the graph this time forms a square or a rectangle. So you just do the base times by the height in order to get the area. So the height is 10 and the base goes from 5 to 15, which is also 10, and then so 10 times by 10 is 100 meters. Continuing with Unit 2. This is green here. By the way, if you've got the exercise book that Pearson have created, I'm showing you the lessons that these specification references apply to. So you could look it up at school in your lesson with your teacher if you were revising using the book, or if you've bought a copy of the book yourself. Right, you need to be able to describe a range of laboratory methods for determining the speeds of objects, such as the use of light gates. Right, so if you've never used light gates before, it's basically a gate with a light. Now, you'll put a little card on the back of a car, and as that car goes through the light gate, this card breaks the light and it sets off a timer. So if you know the distance of the card, which is usually about 10 centimeters, you just do 10 centimeters, so that's the distance, and divide that by the amount of time that it took for it to travel through. Another way to get the speed would be simply to measure a distance for one mark, and say you'll measure it with a trundle wheel for another mark, and then you measure the time for another mark with a stopwatch. So that could potentially be 4 marks. And then for a 5th mark, you say get the speed by doing distance over time. You need to be able to recall some typical speeds encountered in everyday experience for wind and sound. Well, wind could be 4 meters per second, which is about 9 miles per hour. Or it could be 10 times that. We've had some 90 miles per hour winds recently, which would be 40 meters per second. Sound is about 330 meters per second, depending on what the density of the air is. And speeds for walking could be 1.4 meters per second. Running is 4 meters a second. Cycling about 6 meters a second, depends if you're going down a hill or not. And other transportation, such as a car, well, if you're going 70 miles per hour on a motorway, that will be 31 meters per second. You need to be able to recall that the acceleration, g, in free fall is 10 meters per second squared, and be able to estimate the magnitudes of everyday accelerations. So make sure you know that gravity is 10. You'll get a mark just for knowing that. Everyday accelerations, well, a person could be accelerating at 2 meters per second squared, and if you've got a car pulling away, it could be 4 meters per second squared. That's not a sports car. You don't need to know that, or that, so let's just skip it, because they're all red. Remember, I'm only focusing on the higher content, which is this column going down here. Right, you need to be able to explain that an object moving in a circular orbit at constant speed has a changing velocity. Now that's because the direction's changing. Remember, velocity is a vector. It depends on size and direction. So if you're going in a circle, you are constantly changing direction. I've showed you the direction of the velocity with the blue arrows. So if you were here, it's moving upwards. And if you're over here, then the direction is going over to the left. Remember, if the object was just moving with a constant speed, even though it's going in a circle, it doesn't matter because speed's a scalar and has only size. You should be able to explain that for motion in a circle, there must be a resultant force known as a centripetal force that acts towards the centre of the circle. So for 1 mark in an exam, you would just be asked to draw this red arrow here and label it as your centripetal force. Make sure that it comes from the object and it acts toward the centre. I've showed you how to draw it if the object was at the top as well, so you get the idea. You've got to be able to explain that inertial mass is a measure of how difficult it is to change the velocity of an object, including from rest, and know that it is defined as the ratio of force over acceleration. Right, so basically we've just rearranged Newton's second law, F equals ma, and we've got it for m instead, so m equals F over a. Now instead of m just being mass, we just call it a fancy inertial mass. And it's to do with how much force is required to get that mass to accelerate. So let's just imagine you had to create an acceleration of 2 meters per second squared. How easy or difficult is that, depending on how big the object is? Well, what if the object's got a 10 kilogram mass? That would need 20 newtons of force in order to create the 2 meters per second squared. If you had a mass that was 10 times bigger, then you'd need a force that was 10 times bigger in order to create the same acceleration. And what if you had an object that was 100 times bigger? Then you'd need a force that was 100 times bigger as well. So in other words, massive objects have huge inertial mass and need a massive force to get them to move, to change direction or to stop. So the way I think about it is a massive oil tanker ship. Think about how much force it would take to get this thing to move in the first place. And once it is moving, think about how much force it would take to get it to change its direction or to speed up or to slow down. So it's got a huge inertial mass because it needs a massive force to get it to shift. You're supposed to be able to recall and apply Newton's third law to equilibrium situations. So Newton's third law basically says for every action it has an equal but opposite reaction. You can identify when Newton's third law applies because there'll always be two forces of the same type acting on two different objects. For example, here's a man here or a woman heading a football. You can see this pink arrow is the force that the force of the head on the ball. I've said 10 newtons, and the ball will also put a force on the head. It'll be equal in size but opposite in direction. If you need any further help with that, I've got a nice little video all to do with Newton's third law. Check it out. You should be able to recall and apply Newton's third law both to equilibrium situations and to collision interactions, and relate it to the conservation of momentum in collisions. So if I quickly tie that in with the next thing you need to know here, which is to define momentum and be able to calculate it. So momentum is mass times by velocity. All that the conservation of momentum means is that the momentum before the collision equals the momentum after a collision. Since momentum is mass times by velocity, we can say that mass 1 times by velocity 1 is going to equal mass 2 times by velocity 2. And that's a handy little equation. If you don't have much experience with that, I've got a canny little video all to do with momentum. As the code over here says, it'll be in my SP2 playlist from the Edexcel exam board playlist. You need to be able to describe examples of momentum in collisions. So for example, trains colliding and pool balls being broke. So when a white ball collides with the rest of the balls. And that's also on my collision video. You need to be able to use Newton's second law as force equals the change in momentum over the time taken. So they've just slightly rearranged Newton's second law. So the impact force equals the change in momentum divided by the time. And I'm just showing you here how we start off with Newton's second law. Force equals mass times by acceleration. Remember, acceleration is v minus u over t. So if we take a out and we'll pop that in, that's how we end up with this equation here. Multiply out the brackets and there you are. But remember, you're going to be given all of these equations in the exam this year. And again, if you don't know how to use this equation, check out my collisions video. You need to be able to explain methods of measuring the human reaction times and recall typical results. It'll only be worth 1 mark, so I've probably gone over the top here. But basically, you would have a stimulus such as a light coming on, and then the person would need to press a button to turn the light off. That would be the human's response. So the human reaction time is the time between the stimulus and the response. In other words, it's the time between the light coming on and the person smacking the button to turn it off. Right, continuing with Unit 2, so from the book we're up to SP2G now. You should be able to recall that the stopping distance of a vehicle is made up of the sum, which means you add, the sum of the thinking distance and the braking distance. In other words, the total stopping distance equals the thinking distance plus the braking distance. Remember, the thinking distance is the distance that you travel while you're thinking about pressing the brakes during your reaction time, and the braking distance is the distance you travel once you've pressed the brakes. You need to be able to explain that the stopping distance of a vehicle is affected by a range of factors. So, in other words, lots of different factors that affect either the thinking distance, the braking distance, or both. So I've broke them down for you. If it's underlined in red, that means it is a factor that affects the braking distance. And if it's underlined in green, that means it's a factor that affects the thinking distance. So the mass of the vehicle, if you've got a heavier vehicle, it's going to take longer to brake. If you are travelling at a higher speed, that is going to affect the braking distance and the thinking distance. Although it will not affect your reaction time, if you are going faster, you will travel further in the same amount of reaction time. The driver's reaction time, if you are under the influence of alcohol or drugs, or if you're being distracted, or if you're tired, that will increase your thinking distance because it'll increase your reaction time. And what I mean is instead of being able to react in quarter of a second, you might not be able to react until half a second. The state of the vehicle's brakes is a factor that affects your braking distance. The state of the road, so if it's wet or if there's gravel or if it's icy, and also the friction between the tyre and the road surface. If you've got more friction, then you can stop quicker, and if you've got less friction, then it's going to take longer to brake. If you're not too sure about any of that, I've got a nice little video in my SP2 playlist under the Edexcel playlist. This just says describe the factors affecting a driver's reaction time, including drugs and distractions, which I've already mentioned. Remember, these are only worth 1 mark, or they're not even going to be asked anyway. It's just good to know because it complements some of the green areas of the advanced notice article. You should be able to explain the dangers caused by large decelerations and estimate the forces involved in typical situations on a public road. Well, the dangers caused by large decelerations is injury and death. Estimate how the distance required for a road vehicle to stop in an emergency varies over a range of typical speeds. Well, basically, the faster the speed, the greater the thinking distance and the greater the braking distance. So I'm not giving you any particular values, I'm just giving you the common sense approach. You should be able to carry out calculations on work done to show the dependence of braking distance for a vehicle on initial velocity squared. In other words, the work done to bring a vehicle to rest equals its initial kinetic energy, as I'm showing you down here by the equations. So this is a handy little derivation. If you know how fast the car is initially moving and the mass of the car, you can work out the force required to stop it if they tell you a certain distance. Or if they tell you the force, then you can work out how much distance it's going to take for the car to come to a stop. Right, let's start to cover SP3, the third unit, which is called Conservation of Energy. So you can see here this is all green. We've got a couple of little bits of red on the bottom. You need to be able to recall and use the equation to calculate the change in gravitational potential energy. In other words, use this equation here. Delta GPE, so the change in gravitational potential energy, equals mass times by gravity times by height, or change in height. You should be able to recall and use the equation to calculate the amount of energy associated with a moving object. In other words, you need to be able to calculate the kinetic energy using this formula here. Kinetic energy is a half mv squared. Remember to square the velocity first, then multiply it by the mass, and then half the whole thing. Draw and interpret diagrams to represent energy transfers. So here is an energy transfer for a bulb. Electrical energy is going in, light energy is coming out, and heat energy is also coming out. You've got to be able to explain what is meant by the conservation of energy. It just means what goes in must come out. And you can see that from this diagram, 200 joules of energy went in, so 200 joules of energy had to come out. Even though this heat energy is wasted energy and it's not available for any further useful energy transfers. Analyze the changes involved in the way energy is stored when a system changes, including an object projected upwards on a slope. So if it's moving, that's kinetic energy, and if it's going upwards, it'll get converted into gravitational potential energy, as the object will slow down as it goes higher in the air, as if you were throwing a ball or something. A moving object hitting an obstacle, so that would be the kinetic energy turning into sound energy as it hits the wall or whatever. An object being accelerated by a constant force, well, if it's moving, it's gaining kinetic energy. A vehicle slowing down, well, the kinetic energy that is stored would turn into a store of heat energy instead. Bringing water to a boil in an electrical kettle. So that's obviously electric energy getting turned into heat energy. And that's exactly how I would rate it in the exam. And you don't need to waffle on. Just say the energy, do a little arrow, and it shows what the energy is turned into. Explain that where there are energy transfers in a closed system, there is no change to the total energy in that system. Closed system just means nothing can get in and nothing can get out. Just imagine like being in a prison. The energy at the start equals the energy at the end. So that's the law of conservation of energy. Explain that the mechanical processes become wasteful when they cause a rise in temperature, so dissipating energy in heating the surroundings. It's always the same pattern. You always waste energy as heat and it goes to the surroundings. The exam board love you to use the word dissipate, which just means spreading out. You should be able to explain using examples how in all system changes, energy is dissipated so that it is stored in less useful ways. In other words, as I've just said, energy is wasted as heat and we can't use it for any further useful energy transfers. Explain ways of reducing unwanted energy transfer, including through lubrication and thermal insulation. Lubrication just means using oil on any moving parts to reduce friction. Thermal insulation just means taking a beaker of some hot water or whatever inside and putting some insulation such as foam around it, and you can bang a lid on the top as well. That will also reduce unwanted energy transfers. 3.10. Describe the effects of the thickness and thermal conductivity of the walls of a building on its rate of cooling qualitatively. So we don't need to use any numbers, that will be quantitatively, using quantities. So basically, here's the rule. The rate of cooling will decrease. The object stays hotter for longer, in other words, if you put some thick insulation around it and if the thermal conductivity value is low. So remember, if you're a good conductor, that means that you allow heat to pass through it. So if you've got a thermal conductivity value that's low, it means instead of 100 joules per second going through it, it might only be 10 joules. So it's obviously going to keep your object hotter for longer. You've got to be able to recall and use the equation efficiency equals the useful energy out divided by the total energy in. And finally, you've got to be able to explain how efficiency can be increased. Well, base your explanation on the calculation. If we have more useful energy or less wasted energy, then that is basically going to make the efficiency get higher. So if the useful energy increases, that's going to make the efficiency increase. And that could be for the same amount of total energy. And that would be for the same total amount of energy. So in other words, if you put 200 joules in, instead of just getting 20 joules of useful energy out, if we could manage to get 50 or 60 or whatever out, then that number on the bottom stayed the same. This number on the top got bigger, which would make this number here get bigger. That question is often answered badly by students, so pay attention to what I've just said. Moving on to unit SP4, the fourth unit, which is waves. Recall that waves transfer energy and information without transferring matter. So that's basically just a statement that'll get you 1 mark in an exam, and that's all we need. All of these statements here are just for 1 mark, or not even that. You've got to be able to describe evidence with water and sound waves. It is the wave and not the water or air itself that travels. Right, in the case of water, the water simply bobs up and down as a wave travels. It does not move toward the shore, unless of course it's a tidal wave. And in terms of the air moving, well, if a wave travelled and if the air moved, instead of simply vibrating backward and forward, it would create places with no air. and people would choke if they walk into that area, which simply doesn't happen. So the sound travels, the wave travels, by vibrating the air. The air just moves a little bit forwards and backwards, just like the water moves a little bit up and a little bit down. Define and use the terms frequency and wavelength as applies to waves. Well, frequency is how many waves you've got per second. So if you've got a lot of waves per second, that's a high frequency. And if you've only got a few waves per second, or in this case, one wave per second, then that would be low frequency. The wavelength is the length of a wave. So the way I've drew it here, the easiest way of drawing it is either from peak to peak, that would be the wavelength, or from trough to trough. Use the terms amplitude, period, and wave velocity as applied to waves. So to calculate the period, which is the time period, you do 1 divided by the frequency. Amplitude is basically the energy of the wave. So if you've just got a small wave, you get a small energy, and if you've got a large wave, that's a large energy. And the amplitude is from the central location to the top, or you could go from the center to the bottom. Doesn't really matter. If you're going to get it wrong though, you'll go right from the top right to the bottom, and that is incorrect. That would be twice the amplitude. Period is the time period for one wave to be produced, and the wave velocity is simply the speed of a wave in a given direction. Describe the difference between longitudinal and transverse waves by referring to sound, electromagnetic, seismic, and water waves. So longitudinal would be sound and the S wave. No, I've done that wrong. Let's rub that out. The transverse waves are in the blue. So for a seismic wave, which means an earthquake wave, you've got an S wave, which is the transverse variant, and you've got a P wave, which is the longitudinal variant. Water waves are transverse. These go up and down. All electromagnetic waves are transverse. And your sound and your P wave are the longitudinal waves. Recall and use both the equations below for all waves. So to get the wave speed or velocity, you do the frequency times by the wavelength. Another way of getting the wave speed is by doing distance divided by time, just like you'd calculate the speed for any object that's travelling. Describe how to measure the velocity of sound in air and ripples on water surfaces. Well, you could basically just say get the speed, you do distance over time. For 1 mark, I've probably gone over the top here with my explanation, but one way that you could measure the velocity of sound in air is you get someone with a starter pistol to fire it and get someone with a stopwatch. Start the stopwatch when they see the bang and stop the stopwatch when they hear the bang. Make sure that you measure a large distance, somewhere in the region of 500 meters. Measure it with a trundle wheel. Why do I want to do that big distance? Well, it decreases errors due to human reaction time. It increases the accuracy of your timing. Remember, sound travels about 330 or 340 meters per second. So by making the sound travel 500 meters, you're going to have somewhere between 1 and 2 seconds in order to start and stop your watch. Calculate the depth or distance from time and wave velocity. Well, distance is velocity times by time. So I've just rearranged the equation. Describe the effects of reflection. Well, that just means bounce, like that. Refraction, well, that just means bend when it enters a different material. Transmission means to pass through, and absorption of waves at material interfaces means it goes in but doesn't come out, just like that. If the wave had energy, which it will have, then that energy is now in the substance and the substance will heat up. And explain how waves will be refracted at a boundary in terms of the change of direction and speed. So we're talking about this picture over here. And what I like to do to summarise it is basically say that as the wave slows down, it bends toward the normal. So the light is originally travelling through air, which is a gas, which is less dense. And as it travels into glass, which is more dense, it's going to slow down because there's more atoms in its way. As it comes out the other side, it's going to go from glass into air, so it's going to speed up. And as the wave speeds up, it bends away from the normal. You can see that I've labelled the normal, which is just an imaginary line at 90 degrees to the surface. And you get your angle of incidence between the ray and the normal, and your angle of refraction between the ray and the normal. Unit 4 continued. Recall that different substances may absorb, transmit, refract or reflect waves in ways that vary with wavelength. Well, the factors are the density of the material and the stiffness of the material. So in other words, if a wave's trying to go into a material, if it's going into a hard, stiff wall, it'll probably go in. But if it's trying to get into some soft, floppy curtains, then it'll just get absorbed and it won't transmit through. So the type of the material definitely determines whether the wave gets absorbed, transmitted, or refracted or reflected. Describe the processes which convert wave disturbances between sound waves and vibrations in solids, and explain why such processes only work over a limited frequency range. Well, we're only interested in the audible range of humans, which is between 20 Hz and 20,000 Hz. So sound waves are longitudinal. Now, how do they get into materials? Right. Well, the sound waves cause pressure on the surface of solid materials, and some energy gets transferred into the material. Use this to explain the way the human ear works. Right. Well, the vibrations would get detected by tiny hairs in the cochlea. They create electrical impulses which travel along the auditory nerve to the brain. Recall that sound with frequencies greater than 20,000 Hz is known as ultrasound. Well, you'll get 1 mark for knowing that. Recall that sound with frequencies less than 20 Hz is known as infrasound. Again, 1 mark for that in an exam. Explain uses of ultrasound and infrasound, including sonar, which is ultrasound, fetal scanning, which is ultrasound. Fetal scanning is just a posh word for a baby scan. And exploration of the Earth's core. Right, well, that's infrasound. So, if we're using ultrasound for sonar, we're basically, ultrasound wave travels down and back up to the ship, and you can get the depth of the ocean if you half the distance travelled by the wave, because the wave's got to go down and up, but the depth is just down. To get the distance of something, remember, we do the speed of the wave times by the time. So if we just do the speed of the wave times by the time and then half it, or divide it by 2, that'll give us the depth. So make sure that you half it once you've calculated the distance. That's a common mistake by students. How do we use ultrasound for baby scans? Well, it's exactly the same thing. Send a pulse of sonar in and it reflects off the baby and comes back. We get the depth by doing speed times by time divided by 2, and then there'd be an image built up on a computer screen, depending on the depth. Describe how changes, if any, in velocity, frequency and wavelength in the transmission of sound waves from one medium to another are interrelated. Right, so they're basically just saying that the wave's velocity changes if the frequency and wavelength changes. However, for a specific example, do you know that the frequency of sound stays the same through air and through solids? So if a sound was travelling through air and then went into a solid, the frequency would just stay the same. However, the velocity would change. So this must be due to a change in wavelength. So the wave velocity is the frequency times by the wavelength. In other words, if the wavelength increases, the velocity increases, and if the wavelength decreases, then the velocity decreases. So velocity, frequency, and wavelength are all interrelated. Change one of them, and it'll change something else. Unit SP5, the fifth unit from paper 1, which is about light and the electromagnetic spectrum. You've got to be able to explain with the aid of ray diagrams reflection, refraction, total internal reflection, including the law of reflection and the critical angle. So over here you can see refraction is when the light is bending, or any wave is bending. At the critical angle, the light travels along the interface of the surface. So as the light is entering, and the light is bending, and it's going right along here. Now you can see there's some partial reflection there. That's the critical angle. Above the critical angle, you get total internal reflection happening, where all of the light gets bounced back inside. All of the light, hence total internal, because the light is bouncing inside, and it's reflection because it's reflecting off the back surface. If we pop over here, you can see reflection, I equals R, and that's the law of reflection. So bouncing off a mirror here, the angle that the light comes in at is the same as the angle at which the light bounces off at. I is the angle of incidence, R is the angle of reflection. And that's an example of specular reflection, which is what the next lesson objective is about. Explain the difference between specular and diffuse reflection. So specular reflection happens off a flat, smooth surface, and diffuse reflection happens on a rough surface where the light is getting scattered all over the place. Explain how colour of light is related to the differential absorption at surfaces. If white light comes down, which is a mixture of all the colours, an orange object looks orange because all the other colours get absorbed and orange is reflected. So that's why the object appears orange. If the object was red, then all the colours except for red would get absorbed and red would be reflected. Transmission of light through filters. Well, whatever colour the filter is, it lets that colour through and only that colour. So a green filter only lets green light through. Relate the power of a lens to its focal length and shape. So if you've got a skinny lens, a thin lens, it's got a low power and you'll end up getting a long focal length. When I'm thinking about the power, I think about the power at which it bends the light in to the focal point. You'll notice I have drawn the focal length. This lens here is thick lens. I like to think about it as being like a bicep. If you've got a thick bicep, it's very powerful. It brings the light in very quickly to a focus. So thick lenses got a high power, you get a short focal length. Use ray diagrams to show the similarities and differences in the refraction of light by converging and diverging lenses. So a converging lens is thick in the middle and thin on the edges, and it converges the light, which means it brings it together. Divergent lens is thin in the middle and thick on the edges, otherwise known as a concave lens. This is a convex lens on the top. The concave lens is a divergent lens, which makes the light spread out. The focal length here would be back there. If you don't know much about lenses, check out my video all to do with lenses, and it'll be in the SP5 playlist in the Edexcel exam board playlist. Explain the effects of different types of lens in producing real and virtual images. A virtual image cannot be projected onto a screen for 1 mark. A real image can be projected onto a screen. And again, if you're not too sure about some of these phrases, then watch my video to do with lenses. Especially if you don't understand what magnified, diminished, erect and inverted means. Recall that all electromagnetic waves are transverse, that they travel the same speed in a vacuum. You can see we've turned into yellow, so that's literally a statement for 1 mark that you need to know. Explain with examples that all electromagnetic waves transfer energy from the source to the observer. We don't need to bother with this core practical. For the higher, it's in red. Recall the main groupings of the continuous electromagnetic spectrum. So I've drew it down the bottom. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. And you've got to know that they are grouped in order of decreasing wavelength and increasing frequency. In other words, the waves over this end of the spectrum have got low frequency, low energy and a long wavelength, and as we're moving across to these waves over here, they've got higher frequency, higher energy and short wavelength. Unit 5 continued. We don't need to know any of that stuff there. And just as a light touch, we need to know these. So you've got to know the potential dangers associated with an electromagnetic wave and how it increases with increasing frequency. So like I've just said, X-rays and gamma rays are the most dangerous because they've got the highest frequency and the highest energy. You've got to know the harmful effects on people of excessive exposure to electromagnetic radiation, including microwaves. They can cause internal heating of body cells. Infrared waves. They can cause skin burns. Ultraviolet waves. They do damage to surface cells and eyes, which just means skin cells. It leads to skin cancer. Don't just say cancer, say skin cancer for ultraviolet. And eye conditions. You know, if you get a lot of bright light in the eyes, it could damage your eyes. If you get a lot of bright ultraviolet into the eyeballs, it damages your eyes as well. X-rays and gamma rays, they can mutate and damage cells and cause cancer in the body. Don't just say it causes cancer. Make sure you say it mutates the cells or damages the cells and causes cancer. You've got to be able to describe some uses of electromagnetic radiation. Radio waves is used for communications. Microwaves is used for communications and cooking and communicating specifically with satellites. Infrared is for cooking and for thermal imaging. Infrared goggles, it's for television remote controls and optical fibres. There's plenty of examples there. Visible light, an example is photography or watching the telly screen. Ultraviolet is for security marking, detecting forged banknotes. X-rays is for medical scans and checking inside of other objects. Gamma rays is for sterilising food and medical equipment. and detection of cancer and its treatment. You've got to recall that radio waves can be produced by or can themselves induce oscillations in electrical circuits. In other words, they make the electrons oscillate backwards and forwards. It's only worth 1 mark, so I'm not going into it. You just need to know that statement. And you've got to be able to recall that changes in atoms and nuclei can generate radiations over a wide frequency range and be caused by absorption of radiations. In other words, gamma rays or X-rays can change the atoms or the nuclei in the nucleus when they get absorbed. SP6, which is Unit 6, Radioactivity. You can see these first few statements here are only worth 1 mark, mightn't even be on the exam. And these green ones here have got a bit more chance of being on the exam. So, describe an atom as a positively charged nucleus consisting of protons and neutrons. Well, that's why it's positive, because it's got the protons in there. Surrounded by negatively charged electrons, with the nuclear radius much smaller than that of the atom, and with almost all of the mass in the nucleus. Recall the typical size or order of magnitude of atoms and small molecules. So the radius of an atom is 1 times 10 to the minus 10 meters or thereabouts. So if you've got a molecule and it's made of 3 atoms, then it's going to be 3 times 10 to the minus 10 meters. The radius of the nucleus is 1 times 10 to the minus 15. So going from 1 times 10 to the minus 10 to 1 times 10 to the minus 15, the nucleus is 100,000 times smaller than the radius of the atom. If you need help with any of these videos, then go on my SP6 playlist. Describe the structure of nuclei of isotopes using the terms atomic or proton number and mass or nucleon number, and using symbols in the format 136C. In other words, the mass number on the top, proton number or atomic number on the bottom, and the symbol to the side. Recall that the nucleus of each element has a characteristic positive charge, but that elements differ in mass by having different numbers of neutrons. In other words, it's explaining an isotope. Right, you basically say an isotope's got the same number of protons, but a different number of neutrons. Thank you very much, 2 marks. Recall the relative masses and relative electric charges of protons, neutrons, electrons, and positrons. Right. These are the particles: proton, neutron, electron, positron. The relative masses of each one are wrote there, and the relative charge is wrote there. Protons are positive, neutrons are neutral, electrons are negative, positrons are positive. Protons and neutrons have got a relative mass of 1. That's why they are in the nucleus, and that's why most of the mass of an atom is in the nucleus, because they're little electrons orbiting around the outside are nearly 2,000 times less mass. 1 divided by 1,835 is a quote from the book. You've got to recall that in an atom, the number of protons equals the number of electrons, and it is therefore neutral. Recall that in each atom, its electrons orbit the nucleus at different set distances from the nucleus in shells, in other words, just like that, the Bohr model. Explain that electrons change orbit when there is absorption or emission of electromagnetic radiation. The electrons will jump up a shell if they absorb electromagnetic radiation, and they will drop down a shell if they emit electromagnetic radiation. Explain how atoms may form positive ions by losing outer electrons. That is just simply a statement for 1 mark. Recall that alpha, beta minus, beta plus, the positron, gamma rays and neutron radiation are emitted from unstable nuclei in a random process. So in other words, all those forms of radiation come from the nucleus, and you can't work out when they're going to come out because it's random. Recall that alpha, beta minus, beta positive and gamma rays are ionizing radiations. In other words, it means they can remove electrons from atoms if they bump into the electrons. Explain what is meant by background radiation. Well, it's radiation in the environment all around us all the time. Nothing you can do about it. Describe the origins of background radiation from Earth and space. Let's have a look. Basically, you've got to break it down into man-made sources of background radiation and natural. Man-made sources could be from medical, X-rays, gamma rays, treating cancer, nuclear power stations or nuclear bombs. And sources of natural could be cosmic rays from the sun and radon gas. There are more sources. Check out my video on background radiation if you need to know more. Describe methods for measuring and detecting radioactivity limited to photographic film and a Geiger-Müller tube. Well, Geiger-Müller tube clicks when it's detecting radiation, and a photographic film turns from transparent to black if it detects radiation. Recall that an alpha particle is equivalent to a helium nucleus, a beta particle is an electron emitted from the nucleus, and a gamma ray is electromagnetic radiation. These are the keys to the kingdom. There's your alpha, represented as a helium nucleus. There's the alpha just represented as the alpha. The numbers are still the same, 4, 2. Here is your beta minus particle, 0 mass, minus 1 charge. And here's your gamma, 0 mass, 0 charge. And just in case you didn't know, your alpha is a mass of 4 and a charge of plus 2. That's because there's 2 protons. Compare alpha, beta and gamma radiations in terms of their abilities to penetrate and ionize. In terms of penetration, gamma has got a high penetration. It goes straight through paper, straight through aluminium, and it needs thick lead to stop it. Beta has got a medium penetration. It goes straight through paper, but is stopped by about 3 millimeters of aluminium. And alpha has got a low penetration. It can't even get through paper. Goes about 1 or 2 centimeters in air. Beta goes a couple of meters in air. And gamma goes infinite in air, just about. The ionization powers. Gamma is low ionization. Doesn't really knock many electrons off atoms. Beta is a medium ionization power, so that can knock more electrons off atoms. And alpha is high ionization power. It knocks lots of electrons off lots of atoms. Describe how and why the atomic model has changed over time, including reference to the plum pudding model and Rutherford alpha particle scattering leading to the Bohr model. Well, we'll start off with the billiard ball model really, and then from there we go to the plum pudding model from J.J. Thomson. He said that an atom is basically positive all over the place, and then there are little localized areas of negativity. Rutherford came along with his alpha scattering experiment and he discovered the nucleus. So he said that the protons and the neutrons were in the centre. All the mass was in the centre. And it was Niels Bohr who came along and discovered the shells. The evidence for that was the absorption spectrum and the emission spectrum. I've got a nice little video all to do with that in my SP6 playlist, to do with both the history and the electrons in orbits. Describe the process of beta minus decay. Well, it's a neutron becoming a proton plus an electron. So to visualize it, you got the neutron splitting up to become a proton and an electron, but the electron is not a normal electron. It comes from the nucleus and it's high speed. So it's what we call a beta minus particle. Now, if you look at the mass numbers on the top, these mass numbers on the top on the right should equal the mass number on the top on the left. And this bottom number on the left should equal these bottom numbers on the right. So 1 plus minus 1 is 0, which is 0 there. And 1 plus 0 is 1, which is what we started with. Good. You got to describe the process of beta positive decay, which is your positron. That is when a proton becomes a neutron plus a positron. Again, I'm trying to represent it here for you. So a proton splits up, becomes a neutron, and releases the positron. Explain the effects on the atomic proton number and mass nucleon number of radioactive decays for alpha, beta, gamma, and neutron emission. So, if a radioactive isotope decays and gives off alpha, the atomic number, hashtag means number, the atomic number decreases by 2 because it's dishing out 2 protons, and the mass number decreases by 4 because the mass of an alpha is 4. Beta minus decay, the atomic number would increase by 1, and that's because a neutron is turned into a proton. The mass would be no change though, because remember, a neutron's got a mass of 1, but a proton's got a mass of 1 as well. For gamma, there'd be no change in the atomic number and no change in the mass number, because gamma is 0, 0. And I need to put on the neutron. Atomic number, no change. But the mass number would decrease by 1. Unit 6 continued. You can see it's all yellow for the higher. So we're just wanting to pick up the odd little mark here. Explain that the half-life of a radioactive isotope is the time taken for half the undecayed nuclei to decay, or it's the time taken for the activity of a source to decay by half. I prefer the blue way to say it. Explain that it cannot be predicted when a particular nucleus will decay, but the half-life enables the activity of a very large number of nuclei to be predicted during the decay process. So in other words, you can't tell when one little decay is going to happen, but you can average it if you've got a large number of decays happening. Use the concept of half-life to carry out simple calculations on the decay of a radioactive isotope, including graphical representations. I'm not going into the detail of that. You'll have to watch my half-life video. Describe uses of radioactivity, including, household fire or smoke alarms. In other words, so smoke alarms, we use alpha radiation. For irradiating food, use gamma. Sterilizing of equipment, such as medical equipment, use gamma. Tracing, use gamma. If you don't know what a tracer is, you'll have to check it out. I don't think I've made any videos to do with that. Gauging the thickness of materials, that's beta. And diagnosis and treatment of cancer, that is gamma. Describe the dangers of ionizing radiation in terms of tissue damage, possible mutations, and relate this to the precautions needed. Precautions needed to minimize the time spent close to the radioactive source. In other words, stay away from the radiation. If you do have to get close and pick it up, handle it with tongs, big scissor things. Wear a lead apron, which is what we call shielding. Wear a dosimeter badge to record your exposure. Explain how the dangers of ionizing radiation depend on half-life and relate these to the precautions needed. Well, if you are injected with a tracer to see what's going on inside your body, It should have a short half-life, so it doesn't stay radioactive for long. Otherwise it'll cause damage. Explain the precautions taken to ensure the safety of people exposed to radiation, including limiting the dose for patients and the risks to medical personnel. Well, that's what I said before. Make sure if you are the medical personnel, you are doing all of these things. And the precautions for the patient is to make sure that the radiation has got a short half-life and then it gives off gamma, so it can easily get through your body cells without ionizing them. Remember, gamma was the least ionizing of the radiations. Describe the differences between contamination and irradiation effects and compare the hazards associated with these two. Well, contamination is when you have the particles of radiation on you or in you. Irradiation is just when you were exposed because you were close to a radioactive source. Once you move away, the irradiation stops. Explain some of the uses of radioactive substances in diagnosis of medical conditions, including PET scanners and tracers. So you just say radioactive substances can be used in PET scanners and tracers. Explain why isotopes used in PET scanners have to be produced nearby. Well, that's because they must have a short half-life if you're going to inject them into the patient, and yet they still need to be powerful enough so that the medical staff can get the results required. That's why the tracers need to be made or produced nearby. So you can quickly get them to the hospital, quickly get them used, and then they decay. Evaluate the advantages and disadvantages of nuclear power for generating electricity. So the advantages are the lack of carbon dioxide emission, and the disadvantages would be the risks, the public perception, and the waste disposal and safety issues. Recall that nuclear reactions, including fission, fusion, and radioactive decay, can be a source of energy. Explain how the fission of uranium-235 produces two daughter nuclei, and the emission of two or more neutrons accompanied by a release of energy. Obviously, you don't need to explain it because it's only worth 1 mark. You just need to basically say what I'm underlining. Explain the principle of controlled nuclear chain reaction. Right, well, we control it by using boron control rods. Explain how the chain reaction is controlled in a nuclear reactor. Well, yeah, we use moderators and control rods. Describe how thermal energy from the chain reaction is converted into electrical energy in a nuclear power station. So, yeah, what happens in a nuclear power station? You just say heat energy gets converted into electrical energy. 1 mark, thank you very much. You got to say that the products of nuclear fission are radioactive. You've got to say that nuclear fusion creates larger nuclei accompanied by a release of energy, and fusion is the energy source for stars. You've got to explain the difference between nuclear fusion and nuclear fission. Well, nuclear fission is large nuclei splitting up and releasing energy, and nuclear fusion is small nuclei joining together and releasing energy. Explain why nuclear fusion does not happen at low temperatures and pressures due to electrostatic repulsion of protons. Well, I mean, that's just the statement, isn't it? That's the question, but that's also the answer. You know, why doesn't nuclear fusion happen at low temperatures and pressures? You just say because of electrostatic repulsion of protons. You've got to be able to relate the conditions for fusion to the difficulty of making a practical and economic form of a power station. In other words, a nuclear fusion power station is very expensive because you've got to create the high temperatures required for fusion. So that takes a lot of money to create that very high temperature. It's just not economic. Economic means to do with money. So in other words, it might cost 200 quid and you're only getting 180 quid's worth of electricity. There's no point wasting your money. Costs you more money to make the electricity than you do to sell it. It's not economic. And finally, SP7, so Unit 7, Astronomy. We don't need to know any of that stuff there, so let's start from here. You've got to be able to compare the steady state and Big Bang theories background radiation. So cosmic microwave background radiation. So the steady state theory basically says the universe has always existed and will never end. The universe is expanding and extra matter is constantly being created, and the universe density stays roughly constant. That's because as it gets bigger, more matter is being created, according to that theory. The Big Bang theory says that the universe has a finite age, so in other words, it was sort of born and then one day it'll cease to exist. It started as a singularity, which is a very small, infinitely dense single spot in the universe. One day there was a Big Bang, and the singularity expanded, and still is. So in other words, it's got an expanding universe part of the theory. Describe evidence supporting the Big Bang theory, limited to the red shift and cosmic microwave background radiation. So the evidence supporting the Big Bang theory is the red shift. Now what that basically means is that it's evidence that the universe is expanding. You've got to recall that as there is more evidence supporting the Big Bang theory than the steady state theory, it is the currently accepted model for the origin of the universe. So for the Big Bang theory, you've got two lots of evidence. You've got evidence of the expansion, and you've also got evidence of the bang. Whereas for the steady state theory, there's only evidence for the expansion. Describe that if a wave source is moving relative to an observer, there will be a change in the observed frequency and wavelength. They're talking about the Doppler effect. So if this object, which is a van, is coming towards this observer, as the sound is coming off it, let's say it was an ambulance, as the sirens are blaring, the front end of the noise is getting squashed together and the back part of the noise is getting spread out. So as the ambulance comes towards you, it sounds high pitched, and as the ambulance was to pass you, then it would sound low pitched. And what we see is that the waves moving towards the observer have shorter wavelength and higher frequency, and the waves moving away from the observer have a longer wavelength and a lower frequency. Explain how both the Big Bang and steady state theories of the origin of the universe both account for redshift of galaxies. Well, that's because they both say that the universe is expanding. So the steady state theory says the universe is expanding, and the Big Bang theory also says that the universe is expanding. So the redshift evidence is good evidence for both. But remember, the Big Bang's got more evidence because it's also got evidence of the Big Bang part, which is the cosmic microwave background radiation. So the Big Bang theory is the most popular and commonly accepted theory. Explain how the discovery of the cosmic microwave background radiation led to the Big Bang theory becoming the currently accepted model. Well, I've just explained that. Describe the evolution of stars of similar mass to the Sun through the following stages. So first of all, there will be a nebula, which is a big dusty cloud of gas in the universe, the remains of a previously exploded supernova probably. Then it will turn into a star, which is the main sequence. Then you'll have a red giant, and then you'll have a white dwarf. I've got a lovely little video about that on my YouTube channel. It is, however, only worth 1 mark-ish because it's yellow. Right, I forgot to tell you about this here. Explain why the redshift of galaxies provides evidence for the universe is expanding. So if this is us on the Earth, If you've got a galaxy and it's only that far away, then it's not moving very fast. Whereas this galaxy here is much further away from us, so it must be moving faster. And what we find is when we observe the redshift from further galaxies, the redshift is larger for the further galaxies compared to the closer galaxies. So more distant galaxies move faster and they have a larger redshift. So that is evidence that the universe is expanding and started from a single point. Describe the evolution of stars with a mass larger than the Sun. If you are larger than the Sun, again, you're going to be a nebula like you were before. You're going to be a star, a main sequence like you were before. But instead of being a red giant, you'll be a red supergiant. And instead of a white dwarf, you'll be either you'll be a supernova. And if you are a big star, you'll turn into a neutron star. Or if you are a massive star, after you've supernovaed, you'll become a black hole. Again, check out my video to do with that if you don't understand. And finally, so if you're still with us, well done. Next, explain how the balance between thermal expansion and gravity affects the life cycle of stars. Well, during the main sequence of a star, the force of thermal expansion pushing outwards would be balanced by the force due to gravity pushing inwards. And it's a main sequence which is stable. However, after the main sequence, the force of the thermal expansion going outwards is smaller than the force due to gravity, so the star would start to collapse, or at least the inner core would, and then the outer parts would blow off. It would first of all swell up as a supergiant. It would swell up as a red giant or red supergiant, and then they'd drift off, or they'd blow up as a supernova. And finally, describe how methods of observing the universe have changed over time, including why some telescopes are located outside the Earth's atmosphere. Well, over time, first of all, we invented telescopes, but they were just on Earth. Then we invented cameras. Then we invented computers so we could map the universe. Then we invented radio telescopes so we could observe different types of waves coming from the universe, not just light waves. And most recently now we've started blasting telescopes out into space on satellites, such as Hubble telescope. So, I hope that's gave you a good idea about what's going to be on your exam, your paper 1. It's your responsibility. If you've identified any weaknesses in your knowledge, thanks to this video, then do something about it. Go away and do a bit of research. The only students who fail these days are the students who don't take responsibility for themselves. So decide to create a great future for yourself by deciding to work hard and be nice. Bye for now.